Welcome to our talk. In this presentation, we will introduce a real-time state estimator for deformable linear objects. Our talk will basically include these four parts. Manipulating deformable objects has great values for a wide variety of robot applications, such as food delivery, cable assembly, and medical surgery. One main part for a successful manipulation is to estimate the state. In this work, we utilize the rope observer with physics engine to represent the rope and to estimate it. The challenges for this approach are twofold. First, point cloud may be missing during the task. Second, the object in the physics engine may fail to track the desired positions, and it will result in some zigzag positions as shown in the right figure. To deal with those problems, we propose a tracking framework that includes a point cloud recovery, node registration, and a nonlinear control module to robustly estimate the state. For point cloud recovery, the goal is to complete the point cloud of the current time frame. And the general idea is to use the information of the previous images. So we first project the current and previous point cloud back to the image plane, denoted as IT and IT-1. Second, we apply the gradient kernel of the images to find the foreground mask. Then, we apply this foreground mask to subtract the foreground and added to the current images. Then we obtain the recovered images of the current time step. In the end, we project these recovered images back to the point cloud and obtain the desired point cloud. After the point cloud was recovered, a node registration module is applied to find a transformation from the node position in the simulator to the current point cloud. The figure illustrates the performance of the proposed structure-preserved registration algorithm, which can robustly estimate even under occlusion and noise. In the end, it comes to a dynamical simulation. In the simulation, the rope is modulated by n nodes, and each node was linked by a spherical joint. So that's similar to how we modulate the robot in the simulator. And we want to move the rope in the simulator to track the desired position, given the registration results. So a controller is needed. Most of the previous work utilized a PD controller to track the position. However, the rope dynamics is nonlinear. It may not be able to achieve a stable performance. We propose to use a feedback linearization controller, which first cancels the nonlinearities of the rope dynamics, and then use a PD controller to stabilize the system. In the end, we show some results with our proposed algorithm. With the point cloud recovery module, the point cloud is always complete, and the tracking performance will no longer be affected by the quality of the point cloud. We also show some tracking performance with the proposed framework. The algorithm is able to achieve a stable performance. If you are interested in this work, please check our paper and our website for more details and videos. Thank you very much.